Our topic is single mode fiber optic sensor for strain measurement. Well, our team members. The main objective is to develop an experimental setup to study and develop a relationship between strain and power speckle in the fiber optic sensor. Although we have an electrical sensor which has advantages like low cost and they are most flexible, but they too have disadvantages like they are not so accurate and they are very moderate in their efficiency. That's why we have moved to fiber optic sensor, which overcome their disadvantages like it's more efficient and it's more accurate. Disadvantages is well known, it's high cost. Our main proposed work is to have the strain and intensity of a light to get a relationship among them, and by using the image patterns that are obtained from the MATLAB, we are going to have an intensity plot. By using the intensity plot and the power speckle, the fiber optic cable is analyzed. This is our main pictograph of the proposed system. Here you can see a diode laser which is a helium neon of 6050 nanometer and 1310 nanometer. It is given to a coupler, and by the coupler it is given to fiber optic cable. A part of fiber optic cladding is removed and the stress is applied over there. Using a Y splitter, we are going to check the output from the optical power meter and through the microscope to get the analysis. This is the work that has to be carried out that I already have said. As I have spoken, the advantages of the proposed system is the intensity and the peaks relationship, and to get a solution which gives the deterioration in the single mode fiber that will improve its efficiency. Here, this is the experimental setup. As I already stated, a single mode fiber of length 100 meter is used. The ends are cleaned for the dash using isopropyl alcohol. It's mounted on an optical rail and in a microscope. A diode laser is mounted on the other end of the optical fiber rail bridge. The distance between the diode laser and the optical fiber is adjusted till the line of sight between them is established. The intensity pattern is observed through the microscope and the webcam. The image is captured and processed by the MATLAB. The estimation of output is by the three-dimensional matrix, which is then converted into a two-dimensional matrix as to eliminate the noise and the interference. While we come to the software module, the intensity pattern is fed to a computer from the microscope using a web camera. The processing is done by the matrix of size 240 x 320 x 3. The resultant image is normalized to analyze. Well, this is the normalized intensity pattern of a single and a multimode fiber. As you can see the left hand side, the distance between any two consecutive peaks is very minimum for a single mode fiber, and for a multimode fiber it is not negligible. So this is the first analysis which is used to differentiate between a single and a multimode fiber. Well, the picture of a 2D diagram also says the same. what I have stated. Well, this is our algorithm. We start by normalizing horizontal and the vertical direction. Two counters are made to get the number of peaks. By analytics, we set the threshold as 30% and the count for the minimum distance. If the threshold is greater than 30%, increase the counter 1, else increase the counter 2. By the end of the procedure, if both the counter values are same and the threshold is also greater than 30%, it is a single mode fiber, else it is a multi-mode fiber. Well, this shows the sensitivity of the fiber. The graph is drawn between number of turns versus output power in dBm. It is for a single mode and a multi-mode fiber. The first two figures are for the 650 nanometer and 1310 nanometer for a single mode fiber, while the bottom two pictures shows the same for the multi-mode fiber. Well, the analysis is repeated for the speckle pattern for a single mode fiber. Here, the analysis is done for the weight applied to this fiber optic versus the output power. Well, this is the same speckle pattern that is repeated for a multi-mode fiber. Well, we come to the conclusion. From the graphs and the stress patterns that are obtained from the images, it is clear for the fiber to be operated as a reliable sensor to measure stress. That suitable pair is multi-mode fiber with laser diode source of 650 nanometer and a single mode fiber with a laser diode of source 1310 nanometer. Further, a simple low-cost experimental setup to analyze the speckle pattern of the light emanating from the optical fiber is reported. After capturing the speckle image, a simple algorithm is proposed to differentiate between single and multi-mode fibers. This approach does not require clearly laser sources and sophisticated systems. Further, this setup can be utilized for identifying any change in light propagation by analyzing the speckle pattern emanating from the fiber. This principle can be utilized for an optical fiber sensor. We have done with this. With the great help and support from our professor Dr. M. Ganesh Madan, we have able to complete this project. I extend my sincere thanks to our guide Mr. Ganesh Madan sir for his kindly support. Thank you to one and all who watched this video.